Okay, somehow we're on unit 5 already. This is the last unit about derivatives. This one is the analytical applications of differentiation. We covered some applications before. This one is a few more. And while there are only 3 applications here, they are big applications. Important ones, long ones. So this content review won't be as short as the previous one. Let's get right into it. So the first application we're going to talk about is what's called the mean value theorem, or MVT. That basically is kind of like the intermediate value theorem for limits. This one's for derivatives instead. It says that if f of x is continuous on the closed interval ab, differentiable on the open interval ab, then there's got to be a value c in that interval such that the derivative at that point is equal to the average rate of change, or the slope of the secant line, whatever you want to call it. But it's just f of b minus f of a over b minus a. That basically says if you have something like a function here, you have an interval where you have a secant line, there's got to be at least one point on that interval where the tangent line, the slope of the tangent line, is equal to that slope of the secant line. Pretty interesting, pretty useful theorem. There's an application of that called Rolle's theorem. And this basically has the same conditions, continuous on closed interval AB, differentiable on open interval AB. But there's also the criteria that f of a equals f of b. So the value of the function is the same. Then there has to be a point C, at least one point C, such that the f prime of C equals 0. So this is also very useful because it tells us when you can expect the derivative to be 0 on an interval. And that is going to be pretty important when we're considering our next application, which we're actually going to get right into. This one's good to know, but the next one is pretty long. It's curve analysis and sketching. We're using derivatives to draw graphs, basically. We're going to start with extrema. Extrema are just maximums and minimums, extreme values on the graph. And there are two types. There's local or relative, and global or absolute. Local is the same as relative, global is the same as absolute. Don't mind me if I just switch them around sometimes. And there are different procedures for finding these two. First, let's deal with local. And before that, let's actually talk about the difference between them. Let's say we have a cubic function like this, right? These two are local extrema because they are extrema in a small interval surrounding them. Both of these. That one's a local maximum, this one's a local minimum. They're also absolute extrema though, because it's the extrema of the entire domain. This one's the maximum value of the entire domain. Now you might be wondering, well, what about this point? That's higher than that, right? But that's going towards infinity. It's not stopping at a certain point, meaning that isn't really valid for an absolute extrema. Now it's different if instead of going to infinity, there were endpoints, closed endpoints, right? It's a closed interval. Then these would be the absolute extrema, absolute maximum, absolute minimum, because those are higher than this and they stop, right? Now, that doesn't mean that endpoints are always going to be the absolute extrema. If it was something like this is still higher than the endpoint, so that's still the absolute maximum. But yeah, it's good to know the differentiation between them. The local extrema can never be endpoints, but the global extrema can be endpoints. Good thing to know. Now, how do you find local extrema? You use what are called critical points. Critical points are points where the derivative is either 0 or undefined. Usually going to be 0, but never rule out the possibility that the derivative is undefined. And local extrema always occur at these critical points. So what you do, you just find the derivative, set it equal to 0, and then you got a list of critical points. Or you find the derivative, find where it's undefined, and you got a list of critical points. Both. You have to do both. Now, there's also absolute or global extrema. And these follow what's called the extreme value theorem, EVT for short. People generally don't use EVT, but you can if you want to. And that basically says is if f of x is defined on a closed interval AB, then there's got to be at least one, there's got to be an absolute minimum and an absolute maximum in an interval. Here, we have a closed interval, and there is an absolute maximum and an absolute minimum. And it follows that absolute extrema always occur at critical points or endpoints. So it can be critical points, like I showed, at local extrema, but it can also be endpoints. But no matter what, a closed interval of a function always has global extrema. Okay, that was nice. But what if the derivative is not equal to 0? What if it's equal to something else? We have other rules for that. And that's if f prime of x is greater than 0 or less than 0. If it's greater than 0, the function, the original function, not the derivative, is increasing. And if it's less than 0, it's decreasing. Now I'm assuming you know what increasing and decreasing are from pre-calculus. You can also deal with things about the second derivative though, and that tells us a bunch more useful information. It can be equal to 0, or it can be greater than 0, and obviously it can be less than 0. If it's equal to 0, it's what's called a POI, a point of inflection. It's basically changing what is called concavity. Concavity is the shape of the graph. It's concave down here and concave up here. That means it's opening downwards in this region, opening upwards in this region. And so this is a point of inflection where it's changing concavity. If the second derivative is greater than 0, it's concave up. If it's less than 0, it's concave down. Now, one thing to note here, going through all of this, is that just because the first derivative is 0 doesn't mean that there is a critical point, or there is a maximum or minimum. There is a critical point. It just doesn't mean that there's an extrema at that point. I'll get to that in a little bit when I'm talking about the derivative test. But same thing with the point of inflection. Just because the second derivative is equal to 0 doesn't mean that there's a point of inflection. It's just likely that there's a point of inflection. There's a special case where there isn't, and I'll get to that in a bit. But before that, how do we apply this when we're looking for stuff about functions? We can use number lines, and they're not your regular number lines. They just have usually a few points on them. You just put down tick marks wherever you find critical points. You have f prime here and f here. Let's say the critical points are -2 and 3. What you're going to do is you're going to find where the derivative is positive and negative on these intervals. You just plug in a value in these intervals. 0 here, -3 here, 4 here. It doesn't really matter, just as long as they're in those intervals. And let's say you get positive, negative, positive. That means positive corresponds to increasing, negative corresponds to decreasing, and increasing. And this is kind of like the shape of the graph. Obviously, it's not exact, but it just tells you that it's going from increasing to decreasing here, which means there has to be a maximum here. It's going from decreasing to increasing, so minimum here. Good to know. A similar thing you can do with second derivative. You find everywhere where the second derivative is equal to 0. Let's just say there's 1.2. You find out where it's positive and negative. Let's say negative here, positive here. That means it's concave down and then concave up. So there is a point of inflection here. It's changing concavity. Now, let's say this was not positive, but instead it was negative. That means it's going decreasing and then decreasing again. That means this is not an extrema. It's not changing the direction of the graph. It's going decreasing and decreasing again. It's like a cubic function where it's decreasing, there's a small flat point, and then decreasing again. This is a critical point, but it is not an extrema. Okay. And finally, we get to the derivative test. We're still on this second application, by the way, curve sketching and analysis. But we need to talk about the derivative test. They're yet another way to find out whether a local extrema is a maximum or a minimum. The first derivative test uses the values of the first derivative. Second derivative test uses the values of the second derivative. Now, the first derivative test says that if the derivative is greater than 0 before the critical point, and then less than 0 after the critical point, basically it's increasing before and decreasing after, then it is a maximum, a local maximum. If it's the opposite way, if it's negative before and positive after, that means it's going from decreasing to increasing, which means it's a local minimum. And finally, if it doesn't change sign, that means it's not a local extrema. If it's positive, then positive, negative, then negative, still not a local extrema. Just like I showed you with the number lines. This is just another way of doing it. Probably a more formal way to do it. Number lines are not generally well received on the FRQ. You might want to do an actual derivative test. Now, this is kind of a pain because while it's only the first derivative, you have to evaluate it at 2 points. One before the critical point and one after, which is a bit of work. Instead, if you can easily find the second derivative, then you can use the second derivative test, which, again, uses values of the second derivative, but only uses one value. At that critical point C, if the second derivative at that point is less than 0, then it's a local maximum. This means that it's concave downwards, and so there's going to be a maximum up there. If the second derivative is greater than 0 at that point, it's going to be a local minimum. And if it's equal to 0, it is not a local extrema. Like I said before, this is the special case where having the first derivative equal to 0 doesn't necessarily mean that the point is a local maximum or minimum. This is just like the cubic function example, where there's this small breather, a horizontal line, that a critical point, but there is no local minimum or maximum. And breathe a sigh of relief. That is it for curve analysis and sketching. Our final application is optimization. Similar to related rates, but a bit different. It's still word problems, and it's when a quantity needs to be maximized or minimized. And you can see why we're talking about optimization after curve analysis and sketching. It's because it relates to maximums and minimums. We just learned how to find those using derivatives. So while I still vehemently argue for the fact that the College Board should organize the applications in a more coherent way, with optimization definitely being in the contextual area or contextual unit, because it is a contextual application, it does make sense that they are taught after the learning of curve analysis and sketching. So, without further ado, let's get into optimization. So we need to maximize or minimize a certain quantity. So first step, determine which quantity needs to be maximized or minimized. Kind of similar to related rates. And then you have to write an expression for that quantity in terms of other variables using a diagram. Again, very similar to related rates. Using a diagram, write an expression relating quantities. Usually it's going to be something like volume needs to be maximized, distance needs to be minimized, time needs to be minimized, area needs to be minimized, cost needs to be minimized, things like that. And now, using that equation, you use the derivative to determine maximums and minimums of that quantity. Now, you have that equation, right? You take the derivative of that equation and then just set it equal to 0 or undefined to see where there are critical points. Now, usually, like I did with related rates, I would give a brief example of it. But that's not necessary here because that is it for the content review. So we're going right into our practice problems. And there is an optimization problem. So I'll do my example there. But first, there is this curve sketching analysis problem. Just when you thought you were done with that. Okay, so we're given this graph here. Find, this is f prime. Find where the function has relative extrema, is increasing, decreasing, a bunch of stuff. Okay, first, relative extrema. Also, this is a very common type of FRQ question, graph analysis. It gives you a graph of f prime. You have to talk about the corresponding function f of x or f double prime of x and things like that. So first, relative extrema is when the derivative changes signs. And that occurs here at 0 and here at 6. Because it's going from negative to positive and then positive to negative. So our answer for part A is x equals 0, x equals 6. Now, obviously on an FRQ, you're going to need to write a lot more than that. You have to say why you're choosing these points. You have to say that it's changing signs and things like that. By the first derivative test, for example. B is increasing or decreasing. So that occurs exactly based on the sign of the derivative. So we said minus positive, negative, positive, negative. And so when it's negative, it's decreasing, positive, it's increasing. So for increasing, we can say it's from 0 to 6. And notice I'm using open brackets here because at 0, it's not really increasing or decreasing. It's an extrema. And then for decreasing, it's going to be negative infinity to 0, u 6 comma infinity. And that u, if you don't know, just means union. So it's just both of these intervals together. C, point of inflection. Well, that's when the function itself changes concavity. And that means that the first derivative has a critical point. Because if the first derivative has a critical point, then the derivative of that is equal to 0. So this has a critical point. You take the derivative of that, gives you f double prime of x, and when that's equal to 0, then f prime of x has a critical point. So that critical point looks to be around x equals 3, and so the point of inflection is going to be x equals 3. Is concave upward or downward? Well, that has to do with whether the original function is, that has to do with the second derivative being positive or negative, and that is directly correlated to whether the first derivative is increasing or decreasing. When the first derivative is increasing, like here, the second derivative is positive, which means that the original function is concave up. Very confusing, I know, but bear with me here. We're almost done. If it's decreasing, second derivative is negative, and so original function is concave down. So concave upwards is going to be negative infinity to 3. Concave downwards is going to be 3 to infinity. And then E, finally, we have, this one is a bit different. We want to draw a sketch of f. Okay, with all that we know here, we might be able to do that. We know that at x equals 0 and 6, at 0 we know it has to be, it's going from negative to positive, which means that it's going from decreasing to increasing, and so that is a minimum. This is going from positive to negative, so increasing to decreasing, that's going to be a maximum. So there has to be minimum at x equals 0, maximum at x equals 6. We know x equals 0 is 1, f of x equals 6 is 5. So 1, 5, something like that. We also know it's increasing between 0 and 6, decreasing everywhere else, which aligns with what we saw earlier, because if it's increasing, that makes sense. Decreasing, that means this is a minimum. Decreasing, that means that is a maximum. That's just a rough drawing, though. We also know that x equals 3 is a point of inflection, so it should be concave up before this and concave down after this. So this is a very rough sketch of what a function would look like. That's all we know so far, but it's actually pretty close. Obviously, exact points are not known, but we can make a rough estimate of what the shape of the graph would look like. And that's what curve sketching and analysis is all about. I'm glad we finally did this example, because all we've been talking about is curve analysis, and now we actually got into curve sketching. We drew a sketch of the original function. Very nice. Okay, last example problem. I know this video is getting a bit long, but this one's optimization, very important problem, because it's basically going to be the only example of optimization we've done. So in open box, you use a piece of cardboard 8 by 15. You cut a square from each corner. This is a very common type of optimization problem. Let's say the side length of the square is x, right? If that's x, then this part in the middle is going to be 8 minus 2x, because there's x on each side. And similarly, this part in the middle is going to be 15 minus 2x. And now if you draw dotted lines, you see that the figure enclosed by the dotted lines is going to be the base of the rectangle, and then you wind these sides upwards. That's what it says. You fold the sides up. You want to find the length of a side of the square being cut. That is x. That's exactly what we want, so that the box will have a maximum volume. So you want to write the volume in terms of x, so that you can take the derivative, find when v prime is equal to 0, and then the x value of that is going to be the length of the side that you want. So how do we do that? We know this box, it's going to be a rectangular prism, which has the formula length times width times height. What are these values, though? Okay, when you first look at the base of this, that is this dotted figure right here. That's length times width. We have 8 minus 2x times 15 minus 2x. And then don't forget, it's volume, not area. And so we're going to want to multiply by the height of the box, which is going to be x, because that is just what you're folding upwards, that has a height of x. And obviously on the AP exam or whatever, you can kind of visualize this on a piece of paper, kind of folding it. You realize that the height of the box is going to be the length of this square being cut. And so let's expand. We do not want to use product rule 3 times. So 8 minus 2x times 15 minus 2x. Okay, 8 times 15 is 120. Negative 2x times 15 is negative 30x. Negative 2x times 8 is negative 16x. Again, brushing up your algebra skills. And then plus 4x squared, all times x. That's just going to be equal to 4x squared times x is 4x cubed. And then this is negative 46x times x is minus 46x squared. And then plus 120x. Now, that's a nice function and all, but what do we do with it? We take the derivative. V prime of x is going to be the derivative. We just use power rule throughout this entire thing. You bring the 3 down, you get 12x squared, minus, you bring the 2 down, you get 92x, and then just 120. You bring the 1 down, it's just 120. And then we want to find out when this is equal to 0. There are a few ways you can do this again. One of them is quadratic formula, one of them is factoring. Honestly, it doesn't really matter what you do. I would do quadratic formula because it's a end-all be-all method, but you can choose whatever you want to do. In this case, I'm just going to factor it out, but on the test I would do quadratic, because on the test you wouldn't know what the factors are. This is just a quicker solution. You would do 4 times 3x minus 5 times x minus 6. And so there are actually two values here. X is equal to 5/3. Again, I'm writing up here so I don't take up too much space. And X is equal to 6. We have to find out when this is a maximum and when this is a minimum. So what do? We use our trusty old second derivative test. You can use a multitude of things. You can use a number line, first derivative test, second derivative test, anything you want. I'm going to use second derivative because that's the easiest to do. V double prime of x is going to be just bring the 224x minus 92. Now you just plug in your different values. Let's start with 6 because that's a bit easier. You have 24 times 6, which is equal to 144 minus 92. That gives you 52, which is greater than 0. And so that is going to be concave upwards, which means it's going to be a minimum. And again, you can try plugging in 5/3. You are going to get a negative answer though. On the AP exam, you definitely should. I'm just skipping it for now because we know there's got to be a maximum. That is going to be your maximum. And so the length of the side of the box that would be a maximum is x equals 5/3. And in this case, it would be centimeters. Now, another way you could have figured out that it would be 5/3 is because 6 is practically impossible. Because if you have the side length of 6, that means that having 2 of those side lengths would just overpass the page. And so that is physically impossible. You cannot have squares of side length 6 being cut from the corners of this box. But yeah, this is the calculus way of proving that. That's, I guess, the geometric or logical way of proving that. Anyway, that's all we had. I know we only had 2 practice problems, but that first one was 5 different parts, and the second one is also pretty long. So made it up for the usual 3 problems. This is more than enough. But yeah, this, like I said, is our last video for derivatives. Next time, we're going to introduce integration. Can't wait.